Ever wonder how your phone knows exactly where you are on this massive spinning rock? Welcome to This Explainer. Today, we're going to break down exactly how we find our place on Earth by building the geographical grid literally from scratch. Whether you're navigating a cargo ship across the ocean or, just dropping a pin on a map app to find a coffee shop, this coordinate system is working quietly behind the scenes. So, we're going to unpack the really elegant geometry that makes the whole thing possible.
Okay, let's take a quick look at our visual roadmap for today. We'll be hitting 1. Mapping our spheroid Earth, 2. Parallels of latitude, 3. Meridians of longitude, 4. Comparing the coordinate lines, and finally, 5. Longitude and time.
All right, let's jump straight into section 1, mapping our spheroid Earth and finding our place. To really understand the grid, we first have to understand our canvas. And the absolutely crucial point here is that Earth is not a perfect sphere. Because it spins so rapidly from west to east, centrifugal force actually causes it to bulge out at the equator. This makes it an oblate spheroid. Actually, here's a fun fact for you. Because of that equatorial bulge, the peak of Mount Chimborazo down in Ecuador is technically the closest point on Earth to space, not Mount Everest. Pretty crazy, right? Now, trying to map a blank, spinning spheroid floating in deep space is incredibly tough without an anchor. There are no corners, there are no edges. Luckily for us, the Earth gives us exactly 2 fixed reference points, the North Pole and the South Pole. And those 2 points form the entire foundation of our geographical grid.
Moving right along to section 2, parallels of latitude, or the horizontal grid. Now that we have our poles locked in, let's start building the horizontal framework. Think about how the equator acts as the largest one of these, what we call a great circle. From there, all the other parallel lines get progressively smaller and smaller as they approach the poles. The equator is just the line drawn perfectly midway between the North and South poles, effectively slicing the globe into 2 equal halves. But the lines running parallel to it, heading up to the top and down to the bottom of the globe, well, they never intersect. And because they slice the Earth into unequal halves, we refer to them as parallels of latitude, or small circles. So if we were to draw these parallels at 1-degree intervals, we get 89 of them in each hemisphere. When you add those up, plus the equator itself, that gives us exactly 179 parallels in total. Now, you might be thinking, wait, why isn't it 90 in each direction? Well, if you picture it visually, that 90-degree mark at the very top and the very bottom, those aren't circles at all. They're simply point locations. They are the poles themselves. So we've got 89 circles up north, 89 down south, plus that 0-degree equator, bringing our horizontal grid lines to exactly 179. Here's something I find super fascinating. Even though the Earth is not a perfect sphere, the distance between these latitudes remains incredibly consistent. We're talking an average of roughly 111 kilometers apart, pretty much everywhere on Earth. Now, if we want to get hyper-precise because of that oblate spheroid shape we talked about earlier, a degree of latitude does change just a tiny bit. It's about 110.6 kilometers at the equator, and it stretches out to about 111.7 kilometers near the poles. But for general, everyday calculations, that 111-kilometer average is a rock-solid measuring stick for any north-south distance. And this is absolutely brilliant, because it shows that these are not just arbitrary lines drawn by some mapmaker. They are precise mathematical angles measured from the very center of the Earth. Imagine slicing the Earth perfectly in half at the equator and putting a giant protractor right at the absolute center of the Earth's core. From there, you measure an angle of 20 degrees upwards toward the north or downwards toward the south. Wherever those 20-degree angles punch through the surface of the Earth, boom, you draw a line parallel to the equator. That is exactly how the 20-degree parallel is born. It's pure, beautiful geometry projecting straight from the core of our planet. All right, let's pivot to section 3, Meridians of longitude, the vertical grid. So we've got the horizontal sorted. Let's build our vertical framework. Unlike those parallel circles we were just looking at, meridians of longitude are equal-length semicircles. They are spaced furthest apart at the equator, and they actually converge or pinch together right at the poles. Since every single one of them has to connect the North Pole to the South Pole, they are forced to meet at the top and bottom. They cut across the equator at perfect right angles. But here's the catch. Because they are all identical semicircles, there's no obvious starting point. We literally needed an international agreement to decide which one would be 0 degrees. That honor ultimately went to the meridian passing through the Greenwich Observatory near London, which we all now know as the prime meridian. Try this mental exercise. Imagine you are standing directly on top of the North Pole, looking straight down at your feet.
From this perspective, your relative directions actually reverse. East goes to your left and west goes to your right. I know, it totally messes with your head because we're so used to flat maps where east is right and west is left. But this top-down view changes the whole game. The vertical line cutting straight down from you represents the prime meridian at 0 degrees, and directly opposite it is the 180-degree line. If you measure 45 degrees to your left, you're hitting the eastern hemisphere. 45 degrees to your right, you're stepping into the western hemisphere.
Okay, section 4. Let's compare these coordinate lines, latitude versus longitude. Before we throw the element of time into the mix, let's really solidify how these two sets of lines interact with each other. It's like a giant puzzle. Latitudes are parallel circles, and we generally use them to figure out temperature zones. Longitudes, on the other hand, converge at the poles, and they are the absolute secret to understanding local time. Remember, the distance between latitudes is basically fixed at roughly 111 kilometers, but the distance between longitudes, that is totally fluid. It starts at a maximum of 111.3 kilometers at the equator, shrinks down to about 79 kilometers by the time you reach 45 degrees latitude, and then completely collapses to 0 kilometers at the poles. So, latitudes help us separate the hot, tropical torrid zones from the freezing polar zones. But longitudes, they hold the key to the clock. Which brings us perfectly to section 5, longitude and time, reading the Earth's clock. So now let's set our perfectly gridded globe spinning from west to east, because the Earth rotates a full 360 degrees in exactly 24 hours. The sun traverses 1 single degree of longitude every 4 minutes. Let's just do that math out loud really quick. 24 hours is 1,440 minutes. You divide that 1,440 minutes by 360 degrees, and boom, you get exactly 4. This means for every single degree of longitude you travel, the local solar time shifts by exactly 4 minutes. And since the Earth spins from west to east, making the sun appear to rise in the east, places east of you will always be ahead in time, and places west of you will always be behind. All right, let's put this math to the test with a real-world scenario to see how time ticks upwards as we look east of the prime meridian. Let's say you're standing in London, right on the line, at exactly midday, 12 o'clock noon. What time is it for someone hanging out in the capital of Bhutan, which sits way over at 90 degrees east? Let's walk through the steps together. We can easily calculate that Thimphu is exactly 6 hours ahead, which makes it 6 p.m. locally. First, we just find the difference in longitude. That's 90 minus 0, so 90. We take that 90 degrees and multiply it by our magic number, 4 minutes per degree. That gives us 360 minutes. To make that a bit more readable, we divide 360 by 60 minutes to convert it into hours, leaving us with exactly 6 hours. Now, because Bhutan is to the east, their sun rose way earlier, meaning we add those 6 hours to our Greenwich noon. And there you have it, exactly 6 p.m. But what if we go the other way? Time decreases as we move west. So let's figure out the time for New Orleans, which is sitting on the complete opposite side of our grid. Once again, we start at 12 noon at the prime meridian, but this time we're looking out across the Atlantic to the Americas, specifically to 90 degrees west. We're going to use the exact same math, but this time we're subtracting the time, because we are moving west. That means it is 6 a.m. in New Orleans. The longitude difference is the same, 90 degrees. Multiply by 4, you get 360 minutes. Divide by 60, you get 6 hours. But here is the critical difference. Because New Orleans is to the west of Greenwich, the sun literally hasn't reached its peak over there yet. We have to subtract those 6 hours from our 12 noon starting point. That gives us an early morning local time of 6 a.m. Now, I know what you might be thinking. If local time shifts every single degree, wouldn't it be total chaos? Yes. Imagine having to adjust your watch by 4 minutes every time you drove to the next town over. Train schedules, flights, basic communication, it would be an absolute nightmare. So to solve this, countries adopt a central standard meridian. Nations basically just pick a specific meridian that passes roughly through the center of their territory. Whatever the local solar time is on that specific line becomes the standard time for the entire region. It's this incredibly elegant way of blending sheer mathematical precision with, practical everyday living. I really hope this explainer has taken these kind of abstract lines and transformed them into a tangible toolkit for you to understand our world. Think about it for a second. The exact time on the device you are using to listen to this right now, it is directly tied to an imaginary semicircle extending all the way from the North Pole, cutting through your country, and anchored entirely by the spin of an oblate spheroid floating in the dark vacuum of space. Pretty mind-blowing, right? So the next time you look at a map, or honestly, even just glance down at your watch to check the time, ask yourself, how many degrees away is the sun from your standard meridian right now?